Today, Ann and I are going to be talking about ratios, proportions, and rates. I'm going to focus mostly on ratios and rates and talk a little bit about proportions. And then Ann's going to take over and she's going to do some really cool applications involving proportions and rates. And in part of her lesson, she's going to include some geometric shapes. And then Candace is going to finish up talking more about geometric shapes, focusing specifically on angles and triangles. So, as I mentioned, I'm going to be spending a lot of time talking about ratios and rates, and I'm also going to remind you about the set of numbers called the rational numbers. And then I'm just going to introduce the idea of proportions and turn it over to Ann so that she can give you a lot of examples involving proportions. So let's begin by talking about ratios, rates, and rational numbers, and let's begin with an applied example. Customers who order any platter at Uncle Jeb's Chicken Hut have a choice between fries and carrot sticks. Over time, Jeb has noticed that 3 customers opt for fries for every 2 customers who choose carrot sticks. On Friday, 10 people ordered the carrot sticks. Based upon Jeb's observation, how many people ordered fries on Friday? All right, let's kind of think through this with some pictures. In a typical day, for every 3 platter people who order fries, 2 people order carrot sticks. Now on Friday, we know that 10 people order carrot sticks. So what I'm going to do is I'm going to take my little diagram representing 3 fry orders for every 2 carrot stick orders, and I'm going to duplicate it until we have 10 carrot stick orders. And we can see that when we have 10 carrot stick orders, we at the same time have 15 fry orders. Now I'm going to think about this in terms of fractions. And I'm going to make the following observation. That on Friday, there were 15 fry orders and 10 carrot stick orders. I could, if I wanted to, represent this with the fraction 15 over 10. And let's make a little observation here. 5 is a factor of both 15 and 10. And when I pull out the factors 5 over 5, I'm left with the fraction 3 over 2. 15 over 10 equals 3 over 2. Now on Friday, there were 15 fry orders to our 10 carrot stick orders. In general, there's 3 fry orders to 2 carrot stick orders. And it just turns out that 15 over 10 equals 3 over 2. These fractions, 15 over 10 and 3 over 2, are each called ratios. And this equation that says that the ratio 15 over 10 equals the ratio 3 over 2 is called a proportion. Now there's a whole lot of vocabulary there, so let's start digging into the vocabulary. Definition of a ratio. A ratio is a comparison of 2 numbers or 2 quantities. In our ratio, we were comparing the number of fry orders to the number of carrot stick orders. So our ratio was comparing 2 quantities. There are 3 ways we represent ratios. We can represent ratios verbally. We can say A to B. The number of fry orders to the number of carrot stick orders was the ratio 3 to 2. We can represent ratios using a ratio symbol. That's what this colon is. We don't read this A colon B though. We read this A to B. We can also represent ratios with fractions, A over B. So let's put ratios to action. The table below shows approximations of the number of nurses in the United States in 1980 and 1990. Let's compare the ratio of male nurses to female nurses for the 2 years. And these, by the way, are real numbers. I don't mean real numbers in the sense we mean it in the math class. I mean, I actually got these numbers off the internet. So let's move the table out of the way so we have some room to form our ratios. So, in 1980, what we want to do is compare the number of male nurses to the number of female nurses. So the number of males to the number of females was 50,000 to 1,200,000. Now, I'm not going to reduce this fraction all the way, but I am going to make the observation that the number in both the numerator and the denominator ends with 4 trailing zeros. That means that 10,000, that's a 1 followed by 4 zeros, evenly divides into both the numerator and the denominator. And when I divide 10,000 into both the numerator and the denominator, I'm just left with 5 in the numerator, got rid of the 4 trailing zeros, and 120 in the denominator. Again, got rid of the 4 trailing zeros. Let's see what the ratio was in 1990. So in 1990, the number of males to the number of females was 110,000 to 1,800,000. And again, I could divide both the numerator and denominator by 10,000, and this fraction is equivalent to 11 over 180. Now, the question asked us to compare these ratios. How does the ratio 5 over 120 compare to the ratio 11 over 180? Quite frankly, I don't know. So I want to rewrite these fractions in a form that I can make some kind of meaningful comparison. Now, clearly, in both 1980 and 1990, there were lots more female nurses than male nurses. So one way I could make a meaningful comparison between these two ratios is I could figure out for each of the 2 years how many female nurses there were for every one male nurse. And in order to make that determination, I need the numerator of both of these fractions to be 1. So looking at the 1980 fraction, I can make the numerator 1 by multiplying the numerator by the reciprocal of 5, which is 1/5. But in order for me to create an equivalent fraction, I need to multiply by a form of 1, which means that I also need to multiply the denominator of this fraction by 1/5. When I perform these multiplications, I end up with 1 in the numerator. That's a good thing. That was kind of the whole point. In the denominator, I have 120 times a fifth, which is equivalent to 120 divided by 5. So let's see, 5 goes into 120. If my arithmetic part of my brain's working today, that would be 24. So what this ratio tells me is that in 1980, for every one male nurse in the United States, there were 24 female nurses. Let's play the same game for 1990. This time, to get a numerator of 1, I need to multiply by 1 over 11. To maintain equality, I also need to multiply the denominator by 1 over 11. In the numerator, I have 11 over 11, which is 1. In the denominator, I have 180 over 11. This seems like calculator time to me. I'm not quite sure how many times 11 goes into 180. So I'm going to take my 180 and I'm going to divide by 11. And I think if I round this to the nearest tenth and just say 16.4, that will be a number that will allow me to get a meaningful comparison. So by 1990, there were only 16.4 female nurses for every one male nurse. So let's write a nice sentence that kind of summarizes our findings here. In 1980, there were 24 female nurses for every one male nurse, but by 1990, this ratio, pretty cool that I snuck that word in there, eh? This ratio was reduced to about 16.4 female nurses for every one male nurse. Let's see another example using ratios. This time we're going to see an example using a ratio as a rate. Ratios are frequently interpreted as rates. This is especially true in applied problems when the units in the numerator and denominator are mismatched. In other words, when you have one unit in the numerator and a different unit in the denominator. When driven at a constant speed of 60 miles per hour, a Toyunda CR7 can travel 400 miles on 12 gallons of gas. What is the fuel consumption rate in miles per gallon under these circumstances? Well, so miles per gallon as a fraction could be represented as miles over gallons. So to figure out this fuel consumption rate, we need to take the 400 miles and we need to divide by the 12 gallons. Now, when we state rates, we typically like to separate the numerical part of the rate from the unit part of the rate. So the first thing we need to figure out is what is 400 divided by 12? So let's go 400 and divide 12. Now this time I am getting, again, a whole lot of digits, but hopefully you recognize the 0.3333, if it goes on forever, is simply the fraction 1/3. So the numerical part of this rate is 33 1/3, and the unit is miles over gallons. And typically, rate units are one unit over another unit. Since we see this rate very, very frequently, we have an abbreviation for this rate. The abbreviation for this rate is MPG, miles per gallon. The fuel consumption rate for the CR7 is 33 1/3 MPGs, miles per gallon. And one more thing about this example, even if I write the units miles over gallons, I still go ahead and read the unit as miles per gallon. Let's see another example. A 24-ounce container of Alpenmook cottage cheese costs $1.49. The 16-ounce containers are on sale at 2 for $2. Which is the better deal? Well, the trick in figuring this out is that we have two different sizes for containers. Very, very frequently, the way that we make a comparison is we find what is called the unit cost for each of the products. How much does one unit of the 24-ounce container cost, and how much does one unit of the two 16-ounce containers cost? Since the containers are being measured using ounces, our unit is going to be an ounce. We're going to figure out the cost of 1 ounce of each of the containers. So the unit cost of the 24-ounce container is, what I need to do is take the total cost, which is $1.49, and divide by the size of the container, which is 24 ounces. Now again, I want to separate the numerical part from the unit part. First thing I need to do is figure out what is $1.49 divided by 24. So let's go 1.49 and divide by 24. And I see that I get about $0.0621. Now, I don't know about you, but when I'm working with money and the amount of money is under $1, I'd rather work in cents than in dollars. $0.06 is 6 cents. So $0.0621 would be 6.21 cents. So I'm going to go back here. I'm going to change my straight equal signs into squiggly equal signs because I'm approximating. And let's see, the numerical part I came up with was 6.21. And my unit in the numerator is now cents, and the unit in the denominator is an ounce. The unit cost is about 6.21 cents per ounce. 1 ounce of the 24-ounce container cost about 6.21 cents. Let's play the same game for the $2 deal. So the unit cost for the special cottage cheese is, let's see, our total price was $2. We've got two 16-ounce containers, so that's a total of 32 ounces. So let's take our 2, divide by 32, and we get $0.0625, but I'd rather think of $0.06 as 6 cents. So $0.0625 would be 6.25 cents. Since I'm not approximating, I can use what I approximate to be a straight equal sign. And so what do we get? 6.25. Our unit in the numerator is now cents, and in the denominator we have a unit of ounces. So check this out. The 24-ounce container is about 6.21 cents per ounce. The special is about 6.25 cents per ounce. It's close, but the sale is not the better deal. The 24-ounce container is the better deal. So let's go ahead and write a sentence summarizing our results. The 24-ounce container at about 6.21 cents per ounce is still a better deal than 2 16-ounce containers at 6.25 cents per ounce. Let's see one last example. This is another real-life example. The table below shows the amount of U.S. tax paid by married couples filing jointly whose taxable incomes were those indicated in the table. What was the effective tax rate on the $30K, that's a way of saying $30,000 couple in 2003? Before I dig into this problem, I do want to let you know that I dug out my old tax forms, and these are bona fide numbers for married couples filing jointly who have no kids at the time that they filed. So let's get the table out of the way. Let's remind ourselves what the question was. What was the effective tax rate on the $30,000 couple in 2003? So here's our $30,000 column right here, and here's 2003. So this number right here, that's how much tax was paid by the couple. So in 2003, the effective tax rate for the couple whose taxable income was $30,000 was, so let's take the total amount of taxes paid to the U.S. government. That was $4,316. Let's divide out the taxable income. That was $30,000. So let's see, we've got 4,316 divided by 3,000. And that's about $0.144 per dollar. But again, when I'm working with money amounts under a dollar, I like to think in terms of cents. So this is about 14.4 cents per dollar. For every dollar of taxable income this family made, 14.4 cents went to the U.S. government in the form of income tax. Same table. This time we have a different question. Let's focus on the last sentence. It says, use ratios to compare the 2003 tax loads to the 2000 tax loads. Several tax cuts were passed between the years 2000 and 2003. Let's see what the net effect on these tax cuts were for these couples earning two very different incomes. So for the $30,000 couple, or I'm going to call them the 30K couple, The ratio formed by the 2003 tax compared to the 2000 tax is $4,316 divided by $4,504. So let's see, that is, I guess I better figure out what it is before I try writing what it is. So this is 4316 divided by 4504. That's what, about 95.8 cents per dollar? That's a pretty good deal, right? Their taxes went down, what, a little bit more than 4%. They're only paying 95.8 cents in 2003 for every dollar they paid in 2000. Let's see what the deal is for the 200K couple. So their 2003 tax compared to their 2000 tax is $47,446 over $55,049. So let's see, we've got 47446 divided by 55049. 86.2 or 0.862, which would be about 86.2 cents per dollar. So let's see, the couple who earned $30,000 in 2003 paid 95.8 cents for every dollar they had to pay in 2000. The couple who earns $200,000 in 2003 only had to pay 86.2 cents for every dollar they paid in 2000. I wonder who got the bigger tax cut. Well, let's talk about rational numbers. Rational numbers are sometimes described as numbers that can be written as quotients that have an integer in the numerator and denominator. Another way of saying that is rational numbers are numbers that can be written as fractions that have an integer in the numerator and denominator. Well, we have now a third way of saying it. A rational number is a number which can be written as the ratio of two integers. Let's see if the words rational and ratio have anything in common. Oh yeah, they do. The letters R-A-T-I-O. So I guess we could say a rational number is a rational number, but that kind of tied my tongue up, so I think I'm going to move to the next slide. I'm going to finish up with just a little bit of a discussion about proportions. Definition of a proportion. A proportion is an equation that equates two ratios. A over B equals C over D. A over B is a ratio, C over D is a ratio. This equation is equating them, so this is a proportion. Now suppose you encountered this particular equation in, say, a dark alley, and you needed to pacify the equation. Something that you could do is you could eliminate the fractions from the equation, which you could do by multiplying both sides of the equation by B times D. On the left, I have a factor of B in the numerator and a factor of B in the denominator. I could pull out these two factors as a factor of 1. On the right, I have a similar situation. D over D can be pulled out as a factor of 1. And when I pull out these common factors, I'm left with the equation dA over 1 equals BC over 1. This equation is equivalent to our original equation. Hence, A over B equals C over D if and only if dA over 1 equals BC over 1. Now that equation on the right, it's kind of silly to keep these numerators over 1 because dividing by 1 won't affect the numerators. So let's get rid of the denominators of 1. And just because I have a thing about alphabetizing things, I think I'm going to commute the D and A factors and write them as A times D. And here's the property that I want you to remember, that A over B equals C over D if and only if A times D equals B times C. And of course, neither B nor D could be 0 because we don't want to be dividing by 0. That's just not a place we want to go. Now this property actually has a name. It's called cross multiplication. Look at where the a and d come from in the equation on the left. They come from opposite sides of the fraction on opposite sides of the equal sign, as do the b and c factors. We call this cross multiplication, and you'll frequently see people when they're doing scratch work actually draw circles around the numbers that end up being multiplied together. So let's put this property to action. Let's solve 5 over 7 equals 45 over x. If we apply our principle of cross multiplication, we can say that 5 over 7 equals 45 over x if and only if 5 times x equals 7 times 45. Notice that we have indeed multiplied the 5 and the x and the 7 and the 45, but we did it in our heads. Let's go ahead and solve this. We write down our original equation, employing our principle of cross multiplication. 5 times x equals 7 times 45. I could go ahead and multiply 7 times 45, but I think I'm going to go ahead and divide both sides by 5. Because 5 goes into 45 9 times, and 7 times 9 is 63, so I was able to perform this arithmetic without even getting out my calculator. So our original equation seems to be equivalent to the equation x equals 63, whose solution is 63. Let's do a quick check on our calculator to make sure that this solution is valid. I'm focusing on my ratio equation, so the first thing I'm going to do is I'm going to say, okay, what's 5 divided by 7? And that's about 0.714. So now what I want to do is I want to ask myself, okay, if I replace x with 63, is the fraction 45 over 63 about 0.714? So let's do 45 divided by 63, 0.714. We're good to go. The solution is 63. One last example, and it's actually not even a new example. It's the question we started with. Customers who order any platter at Uncle Jeb's Chicken Hut have a choice between fries and carrot sticks. Over time, Jeb has noticed that 3 customers opt for fries for every 2 customers who choose carrot sticks. On Friday, 10 people ordered the carrot sticks. Based upon Jeb's observation, how many people ordered fries on that Friday? Now, I figured this out earlier by drawing some pictures. This time, I'm going to use a proportion. So, in our general ratio, for every 3 fry orders, there's 2 carrot stick orders. On Friday, we don't know how many fry orders there were, but we know that there were 10 carrot stick orders. See how I've organized this in my table? So what I need to do is define a variable to be the number of fry orders on Friday. So I am going to let x represent the number of fry orders on Friday. You probably saw that one coming. So since our general ratio and the ratio on Friday are equal to each other, we can set up a proportion that 3 over 2, the fry orders to the carrot stick orders, equals x over 10, the fry orders to the carrot stick orders. Now, I think I better get my table out of the way so I can finish up this problem. I can use my principle of cross multiplication, which tells me that 3 times 10 equals 2 times x. I can divide both sides of the equation by 2. And that gives me that x equals 15, which is what I figured out with my pictures the first time I encountered this problem. And I also know that 15 over 10 does reduce to 3 over 2. So this solution is good to go. The number of fry orders on Friday was 15. And once again, it's a good thing this is not writing class, it's math class, so we can have some fun with Friday. Now with that, I'm going to turn it over to Anne so she can have some more fun with proportions.